A patient lies on a table, suffering from a kidney stone that needs to be removed. But instead of the traditional scalpel and invasive recovery time, the surgeon reaches for a machine that will destroy the stone from the outside. This device focuses high-frequency sound waves through the patient's body, shattering the stone into dust without a single surgical cut. Hundreds of miles away, a power plant cooling tower stands hundreds of feet tall, designed to manage intense thermal energy and withstand the external pressure of the wind. While these scenarios belong to different fields, their success depends on the exact same equations, the conic sections. We study these shapes in the classroom not for the sake of the graph, but because they provide the specific geometric constraints required to build these technologies. An ellipse is more than a flattened circle. It is a curve defined by two internal points called foci. Any wave emitted from the first focus bounces off the wall, hitting the second focus with absolute precision. This is how a lithotripsy machine works. An ultrasound generator is placed at one focus and the kidney stone at the other. Because the shape forces every sound wave to converge on that single point, the energy passes harmlessly through the patient's skin and soft tissue, only reaching its full intensity once it hits the stone. In this case, the ellipse provides a mathematical solution for a non-invasive surgery that wouldn't be possible with any other shape. A parabola is defined by a single focal point and a fixed line called a directrix. Its geometry allows for the extreme concentration of energy. In this flashlight reflector, placing a light source at the focal point causes light to reflect in perfectly parallel beams. Similarly, a satellite dish captures incoming signals and funnels them directly into a single receiver located at that same focal point. This geometric property also applies to the physics of structural weight. When a suspension bridge cable supports a uniformly distributed deck, gravity pulls the cable into a perfect parabola, allowing it to distribute millions of pounds of tension across its length. Whether the goal is projecting light or spanning a river, the parabola is the shape used to direct and manage force. The hyperbola is the most distinct of the conic sections, consisting of two mirrored curves that face away from each other. Here, the hyperbola is plotted on a coordinate plane, showing how its two branches expand outward. This outward curve solves a specific architectural problem: how to build a hollow, vertical tower that can support its own massive weight while resisting high-speed winds. By rotating this 2D hyperbola, we get a 3D hyperboloid. This design is aerodynamically stable and structurally efficient, which is why it is used for large-scale industrial cooling towers. The hyperbola provides the stability needed for vertical structures to stand tall without collapsing under the pressure of their environment. While these shapes often feel like abstract exercises in a classroom, they are the functional requirements for the technology we rely on. These formulas exist to do more than just plot points on a grid. The ellipse, parabola, and hyperbola allow us to focus sound for surgery, transmit signals across space, and build structures that can withstand the elements. A moment of wonder. These curves are integrated into the cityscapes and industrial sites we see every day. Mathematics is the language used to describe the physical universe, and the conic sections are the specific tools we use to navigate and build within it.